Thanks, Sue. Yeah, it's a great honor and privilege. Now we have not one, there are three scientists who are contributing to this session. Henry Kumar, Santosh, and DrNaresh. So Santosh will be leading the team and they will be presenting on the quantum computing. They're also my ex-colleagues. Feels very nice, good connect with after a long time. So now I welcome Santosh to present the quantum computing.
Sorry, I am an obstacle for you to between you and the lunch. I apologize for that, but I will make it very quick and interactive so that you will not feel that hungry. Just to get to know the audience, how many are students? Good number. From which streams? You are also students.
Yeah.
So which stream?
MCA.
Sorry?
MCA.
MCA. Okay. So your background is most of computer applications, right? And I see few faculties.
Yes.
Faculties are from which the stream?
I'm working for a company.
Oh, okay. Okay. Which company, sir?
Accenture.
Accenture. And you are working on?
I'm working on the data analytics, data engineering.
Okay, right. So other faculties? Okay. So you are working on information science. Fine. Yeah. How many know about quantum? What is quantum? Nobody knows? You have seen the photosynthesis of plants. Are you all aware of photosynthesis? There is a basic thing you would have studied in your, there is quantum in it. So that is where we try to get the, learn from the nature and try to use that to do the computation or to go into the future. For example, how the flight was discovered. We saw the birds flying, right? So using the birds, we thought why we should not fly. We discovered the flight, right? We built the flight. So that is where even quantum also has been evolved, that we are learning from the nature how the atom particles or the electrons will behave and why not use them for our purposes. Like, okay, next slide. So this will be my overall talk. So I will take you to the quantum world, okay? No, go back. Yeah, and see how the evolution of computing has happened. I know that some of the things will be repetitive because Deepika has covered a little, but still, nevertheless, I'll take you on the evolution of computing. Then what is quantum mechanics? My colleague Dr. Naresh, he will speak more technically on quantum mechanics. Then what is the vision? Whom are these quantum technologies are? So I will touch upon that. Then what are the applications of quantum? Then how to get started? So this will be overall my talk. Next slide, please. So Deepika would have covered the first two, classical era, high performance computing era. So I will just go through, through stories so that it will be more interactive with the classical era, then what is high performance computing era, now where we are, the quantum era, and why quantum. So that also I'll touch upon. Next slide, please. Okay, the left one, the astrolabe. Can anybody tell what it is? Actually, it's a small computer. It is from the 13th century. It is from the Roman Empire. It used to predict the motions of the celestial bodies. It was the computer for most of few order of 100 of years until we arrived. The next one was the differential engine. From whom? Charles Babbage. So I don't call it as computer, it is more of less like a calculator. So what was used in that? It was mechanical device was used, like gears, pulleys, right? So using that, he showed us that we can do computation, like addition, subtraction. That is what it started. But that was during the World War I. But during the World War I, Germans sent some encoding messages to the other parties for communication. Are you aware of the encoding messages? Right? If I want to pass a secret to another person, say I want to tell a secret to Renuka Prasad, if I say in plain English, it will not be a secret, right? I will encode, I will say in some other language so that I and he alone will understand. Even a next person intercepts or hears that message, he'll not be able to decode it, right? That is what is encoding. So Germans used this technique for sending the information. But this Charles Babbage computer was not able to decode that. So that time, what happened? Any idea? Have you heard of Alan Turing? Alan Turing machine? No. So that time, the enemies from UK, who are the other parties, what they did was, decoding of those messages to be done, right? So they identified this mathematician called Alan Turing, and he was assigned in charge that you have to decode this message and give it to us. Okay, but he came up with a very another brilliant idea. Okay, if I employ hundreds of thousands of people, still I will not be able to decode. Okay, but what he did was, why not automate this? So I will give you some encoding schemes. This is how encoding is done. Say for example, if there is a message with all alphabets, I will just encode with numbers. Right? 1 to 26, A to Z, I'll just encode with numbers. So this is an encoding scheme. Why not this encoding scheme will be given to a computer or automate this? I'll give the encoding scheme, it has to decode and give the message. So he came up with this encoders. It is called code breakers. So it was based on, again, the registers, tape devices, all those things. So that's where the little modernized computer started. Then came the first general programmable computer. It's a generic computer. Those machines were only for encoding, decoding, or some calculations. But again, programmable one, it came during 1945. It was based on vacuum tubes. Okay. So from vacuum tubes, the next, what we moved on? Sorry? Transistors, right? So it was again a big transistors. It is not a small transistor, it is a big. So the computers which were built using the transistors were of this hall. And there was some dedicated people who have learned to operate that, right? From then on, what we moved on? Programmable chip, where we put all those transistors in an integrated chip, one small chip. You would have used in your labs, right? In some electronic labs, right? So those chips. So that eventually evolved into making a processor. And today our computers, the laptops or desktops are having these microprocessors, right? So that's how the evolution happened. Yeah. Okay. Why high performance computing? Just now you have finished the session on high performance computing. Hope you would have got some idea of why high performance computing. When I have a modern desktop or a laptop computer, why we should go to high performance computing? Right. Very true. Another one? Right. So the datas are huge. The processing speed is not that great. Okay. And the laptops you cannot run for hours or days or years, right? It has to be switched off, switched on. So you cannot do that. So the data are very huge. So, and they cannot scale up this small computer to a very big computer because of power consumption, heat dissipation, cooling, many other things. So what they came up with was build a smaller computer, stack it and make it a bigger computer. Like now I say, if I take one person, he has some energy. Okay. If I combine all the people in this hall, he will have a massive energy, right? So that is what they did, and they come up with stacking all the computers, connecting with network, because during that time the internet, the network evolved from the labs, right? So they made this and they made it as supercomputers. So in India, CDAC, where I come from, so we started this Param supercomputer. That was the first supercomputer, which is Param 8000. Then we moved on to Param Padma, where actually I and my colleague, the ex-colleague Renuka Prasad, we worked on this Param Padma. He was also part of this, and he was managing this. He set up and managed this Param Padma. Okay, so this was of 1 teraflop during 2002-2003. So later on, Param Yuva, NSM, other Param series got added. Okay, now it is into petaflops and exaflops, right? Next. Okay, now we have moved from the Charles Babbage to exaflops, petaflops, exaflops, right? Why we are going to quantum? And I'll just tell you that it is not an upgrade version like how we see from Charles Babbage's computer to the petaflop, where we got upgraded every time. It is not the upgradation. It is another perspective of seeing the data and computing it. Okay? So why quantum? There are some principles, okay, like superposition, entanglement, interference. So this I will leave it to my colleague Naresh to speak on that. But I'll give you the analogy of it, what it is and why. Okay? So quantum is now something like an internet where during 1980s, which were in university labs. Now the quantum is to break out, and the future is quantum. Okay? Oh, no, go back. Yeah. So with quantum, quantum is the tiniest particle where we can use that to do either computation, communication and sensing. Okay? So I said superposition. What is superposition? Any idea? In the layman terms, superposition means what? Placing one on the other, right? Overlap kind of a thing. Okay? So yeah. How many of you seen the Robo movie? Robot? Wow, good number. So you're all movie lovers, right? Okay, good. So in that there is one scene, the Robo, the Chitti Robo, he will take a book and he will read it. How he will read it? He will just scan like this, right? What he is doing? Okay, humans, how you read the books? Sorry? Line by line or page by page, right? But what Chitti did? He just did like this. So what he is doing is, he is reading the pages simultaneously. If there are 1,000 pages, he is reading all the 1,000 pages at the same time. That is the computing power which quantum gives. So you are understanding, right? How much huge quantum, the computing power it is giving, where we can solve bigger problems. I'll tell you the bigger problems. So in communication, okay, there is another um, another thing called entanglement. So what is entanglement? Okay, I see many people from this side. You all go to temples, right? Okay, you all go to temples. What you do, you leave your slipper outside. You go inside the temple. Where will be your mind? Whether on the God or on the slipper? So this is kind of an entanglement. Your mind is on the both places at the same time, right? So how can it be? You're thinking both, right? So this is kind of an entanglement where they say if there is a particle which is entangled with another particle, and even if I take to the moon, I measure or I see what this particle contains, I am sure the other particle in the moon contains another data which I can read, even without going to moon. So you know all that the data cannot be traveled beyond speed of light. True, right? We are using all our fiber optic cables, correct? So that's where we are using the light to transfer the data. That's where we are getting huge speed of data transfer, like in Gbps and all, right? How are we getting? You are using the speed of light, okay? So this entanglement is beyond the speed of light. I sent the another particle to moon, but how to transfer the data? I just have to measure the data here with the particle I own. The other information I know that has been transferred to moon. That is another one. And for communication, they use another property called no cloning. You all know that we cannot be cloned to someone else, like how they show in the movies, right? Dual roles. Okay. So similarly, no cloning is one property that a particle's information. For example, in the classical world, you can copy the data, right? Bits and the numbers, zeros and ones, you can easily copy it. But in quantum, you cannot copy the information. Once you copy the information which it was carrying, the particle, is lost. So you cannot use that particle again, or you cannot send it to other people for communication. So this is where the security of the communication comes in. In the normal, there will be a man in the middle attack, right? So I can take the data which is going through the cable, I can put some decoders, I can extract the information. Right? You know man in the middle attacks? Huh? So, but when the same kind of data is being transferred through quantum channel, even if there is a man in the middle attack, he cannot, or if he reads the data, the other party knows that, okay, it has been tampered, I should not use. Understood? Okay. So, it can also be used in sensing. Some applications where all we can use where all we use the sensors. Sorry? IoT. IoT, where are the applications of IoT devices? Sorry? Okay. This is somewhat the higher level of applications. I'll give you the minute level of applications. You all know that cancer, right? Cancer, it's at what level? Cell level. If I know the behavior, or if I somehow get the behavior of this cell level, okay, and try doing the computation or finding out where it is occurring, how it is occurring, I can prevent it. Correct? So this is because the quantum, the particles which we use for these sensing are very fragile, that it will act on even a smaller sensors. For example, these earthquakes, we are using seismic data for knowing that how much earthquakes and all happen, no? Even now, there are earthquakes happening under the ground, but we are not feeling that. Why? Because that is minute. Even that minute level sensing can be done through quantum technologies. So these are the three areas where you can do the quantum technologies can be used. One is quantum computing, communication, and sensing. Next. Yeah, go back. Sorry? Recent? Yes. Yeah, even that also. That's what I said. In all the healthcares, many things are there. I will come to that later. Once my colleague, he will give about what is quantum mechanics and other properties of it. I will touch upon the applications where all it can be used, and being students, faculties, how you can use those technologies or how you can be taken further. I will now request Naresh to continue.
Hi, I'm Naresh. So I'm working in this domain of quantum computing and communications. So I'll just describe what is this quantum computing and why you should actually listen to this topic now. Okay, as just Santosh mentioned, you see, we're talking about quantum. Says quantum is not actually new. If you school, right, school or maybe early +1, +2, you maybe heard about this word quantum, right? Okay. So where is this quantum thing? Like if you go to the atomic level, right, even in your body, that is called quantum particles. Okay. So quantum is nothing new. So people known this quantum from long time, at least like 115 years. Okay. So from 1900 onwards, and but still people talking quantum now, right? Now what is the reason? See, for example, you take in your laptop. So laptop consists of transistors. So for that, you're working with the quantum particles. Okay, your body works with the quantum particles. Okay, but now what happened is that now there is a lot of advancement in the technologies. Okay, so people call, as I told you, right, when you're talking about a laptop or take a light, laser lights especially. So these are all quantum phenomenon. So what is quantum phenomenon? To just briefly describe, right? If I take this balloon and I throw it away, okay, just throw it away. Now it takes some path, right? So this path we can explain using something called Newtonian mechanics, right? Now you take a rocket, it goes to the moon, right? This can be explained using something called Newtonian mechanics. But which we're talking about quantum particles or the atomic thing scale, right? So they don't obey the Newtonian mechanics. Okay, they obey something called quantum mechanics. Okay. So using those things, so people came with this computer development and the lasers which I'm specifically talking about. Now there is much more advancements. Okay, so people calling this as quantum 2.0. Okay, it's not quantum 1.0. Quantum 1.0 was like at least 80 years old. So quantum 2.0 is what we are talking now. Okay. Now if you look at the last slide, right? So that is actually a quantum computer. You see, that's an IBM based quantum computer. Okay. And the middle part and this part, right? What Santosh has mentioned something about communication aspects and sensing. So for our talk, we will not touch those parts. So we will talk about the leftmost, the rightmost part called quantum computing. Okay. Okay, as I told you, right, now people are talking about this quantum computing. The reason is that the advancement of the technologies. Okay. Now the first term of quantum computing came in the year 1980s. Okay. But the advancements were happened so that if you see across the world, you see starting from the USA, Canada, UK, EU, Israel, India, China, South Korea, Russia, all these companies, all these countries are investing a lot. Why is that? Because one of the reason is that the advantages, what the quantum computing brings to the table. Okay, and basically the security issues. When you talk about quantum communications, so there are underlying threat to their security. So governments felt that we should invest in these particular technologies. Okay. Yes. So in this regard, even in our country, so something called National Quantum Mission was announced in late 2020s, okay, 2018 exactly. So they have announced 6,000 crores for this particular development of these technologies. So which involves development of qubits. Okay, I will come to the part qubits. So you heard this word qubits. Okay. Similarly, for communication side, so there is an development they want, say for example, 2,000 kilometer range. You need to have a communication. Okay. So government was actually funding the organizations to develop these kind of innovations. Okay. And similarly, in the sensing, which Santosh mentioned, and also for the development of materials, so government was actively involved. Okay, apart from the private players. Okay, now I'm slowly going to the quantum computing only. Okay, so this is what certain report says that, like, where could be the with the advancement of the developments, right? So the quantum computing market could be at this range, at this point. Okay, thank you. Maybe I think this point will be covered by Santosh. Okay, what about the education part? Yes. Now, why we should look at the quantum computing first of all? Now, as Santosh has pointed out earlier, so this is the HPC, okay, which we have it in CDAC Bangalore, called Param Utkarsh. Okay. Now we have laptops, okay, but still we already have HPCs. But still people are talking about quantum computing. So why do we require these many things? So when you say HPC, right, so that is the high performance computers, which can solve very complicated problems. Say for example, you want to do the weather modeling. Okay, so weather modeling have a lot of parameters. Okay, now if you give it to the laptop, right, it may take some years and years. Okay, but HPC, say for example, in Indian Institute of Tropical Meteorology, so recently they launched an HPC. Okay, so that computer, right, which can actually in a 5 days time, right, it can actually do the weather forecasting. Okay, but still we are talking about quantum computing. I think he mentioned that point. You see, even a quantum computing comes, it may not be useful for demonstrating the PowerPoint presentation. Okay, we may not use it for like watching movies. So quantum computing is for specific purposes. Okay, it's not like advanced version of HPC. It is a HPCs is a different technologies. Quantum computing is different technologies. So quantum computing is for specific purposes. Okay, so we need to understand what is the specific purposes. So for example, you look at that solving complex problems. So when you say complex problems, say for example, drug discovery and material sciences. Okay, now you see, in the 2-3 years ago, there is something called COVID, right? Now at that time, people are rushing to discover which drug, which will be helpful to cure this problem, right? Now generally for a drug discovery it takes an average of 10 years, but at that time it came to 2 to 3 years, right? Now basically how do you do drug discovery? Say for example, first you want to do the modeling. Okay, these particular molecules are there and this particular catalysis can actually come with certain molecules which can actually cure these kind of problems. Okay. Now as I told you, right, modeling itself is actually challenging. Now there actually quantum comes into the picture. Why is that? In a minute I will talk about that, how quantum computing can actually solve these kind of problems. Similarly, if you look at this financial modeling and cryptography, as I told you, right, why governments are actually interested. So cryptography is one of the domains where quantum computing can actually break these classical encryption methods. Okay, so how can we do that? Okay, so these are several computers. Okay, it's ongoing technologies. So there's supercomputing, quantum computers, ion trap, photonics, and topological. Okay. Maybe next slide. I think already Santosh has covered it. Okay. Now come to these classical computing. What I mean by classical computing? So whatever the computing which you have learned in your MCA, let me call it as a classical computing, and the other computing we'll call it as quantum computing. Okay. Now what are these fundamental unit for computing. We call it as a bits, right? Okay. Now the underlying mathematics for the bits is Boolean algebra. Okay. You have a NOT operations, so the underlying mathematics is Boolean algebra. But one thing, maybe you see, you have given a laptop, you will actually code it, and your system will run and give the output, right? But the important thing we all have to remember here is that computing is physical. Okay, so that is the very underlying thing you have to remember. So what do you mean by computing is physical? Say for example, I'll ask you, say that like 3 into 5. Okay, you'll do the calculation, right? How do you do the calculation? Use your brain to do the calculation. So your brain is physical, right? It has to spend some energy. It has to do some operations in the brain to get the result, right? Now, even your computer, you have transistors. So finally, whatever the inputs you give, if you want to give output, right, it has to do the process the information, right? So this is very important property. Now this comes here. Now maybe you may be aware of this Moore's law, right? Moore's law, are you aware of that? Now if you look at, right, now when Santosh has shown a certain image, now you see if in 1950s, if you have these vacuum tubes, and now if you look at the size of your laptops, you know, mobile phones, right, how narrow it became. Compared to the vacuum tubes, you can do a lot of calculations, you know, just in your mobile phone, right? You can watch movies, you can store memories, you can watch, you see, you can watch live TVs and everything. So how come it possible? You see, because of the advancements, okay? Now, if you look at there, right, now, as I told you, the important point is computing is physical, okay? Now, there comes the quantum computing. Now, what quantum computing does is that, you see, quantum computing will play with the different, what do you call that, the physical systems. Say, for example, we call it as a quantum system. So, what is the quantum system? Say, for example, in the quantum computing, right, the players are electrons, photons. So, these are, as I told you, these are the atomic systems. Okay, so these are the quantum systems which will be helpful for quantum computing. Okay, so you have to understand the fundamental difference is now, who are the players in the quantum computing? It's electrons. It's a atomic systems. Okay, so we use those properties of atomic systems. So how do they are governed? They are governed by quantum mechanics, as I mentioned to you earlier, right? So that's why it's a quantum computing. Is it fine? Yes. So that is a major difference. Okay. Now that is the reason, as I told you, drug discovery, right? Now in drug discovery, what are the things? So drug discovery, it comes to the atoms, molecules. And who are the players? The same atoms and molecules, where quantum computing will have an advantage, because we are playing with their own rules. Okay, electrons and protons and all these atomic systems, right? They will not follow our rules, which is Newtonian mechanics at this level. They follow quantum mechanical rules. Okay, so that's a basic underlying difference. Okay, okay, just a minute here. Now the mathematics, right? So because quantum mechanics, as such, it follows a different mathematical rules. Okay, something called a linear algebra. In the classical computing, we follow something called Boolean algebra. Okay, now that is one of the fundamental difference. And you see, I written some notation there. So zeros and ones, right? As I told you, what are the fundamental units of computing? Bits, right? Zeros and ones. Yes. Now with this quantum mechanical rules comes into picture, what happens is that you say yes or no. Okay, I ask you a question, you tell yes or no, right? It's a 0 or a 1. So there is no intermediate. Okay, it's a 0 or 1. If you want to have intermediate, right, take 2 bits of information. So 0, 0, 1, 0, 1, 1, right? You have 2 bits of information. But what quantum computing, it has an advantage is that it can have a superposition. Santosh has mentioned something called superposition, right? Now if you look at this 0, so that's a funny notation. That's we have that line and that arrow kind of things, right? So to differentiate for us for time being, right, that is for qubits. So what are qubits? Quantum bits. So quantum bits will not, they will follow zeros and ones, but also have an additional layer, something called a superposition. Okay, so it can be in a combination of zeros and one together. Okay, now there comes in advantage. Okay, so the basic gates, right, it will be slightly different to classical computing. Okay, yeah. So these are the two different things which are very reason for your quantum computing. Okay, you can have a superposition. You see, it's not just 0 and 1. You can have an intermediate stage. Okay, so for example, let us look at this point. Now with the 2 bits, right, you actually require 2 qubits. Okay, so let us take 2 bits. So 0 0 0 1 1 0 1 1. Now I give a qubit which is a superposition of 0 and 1. Now you give me 2 qubits. Okay, at the same time it can be in the combination of 0 0. So you just look at like a product. Okay, you take one more qubit. So the first qubit is in superposition of 0 plus 1. Right, you take one more qubit, again 0 plus 1. Now you take the 2 qubits. What will happen? With the 2 qubits, right, it will be in a combination of all these things at the same time. Okay, can you go to the next slide? Okay. Now this is a maze. Okay. Now let us talk that you're starting from here, you have to reach here. Okay. So there are n number of paths here. Right? How do you do? Now you take a pen and then what you will do? You will actually try to take a mark. Right? And you see you come to a dead end and you again start a new path. Again a dead end, again take a new path. So one path you will reach. Right. Now with the superposition, right, what can happen is that because you are in a superposition, you see, you can program your problem in such a way that you can approach all the paths together at the same time. Okay. Now that is what quantum computing gives an advantage. Okay. So in this particular problem, quantum computing can solve even with your compared to your HPC pro systems. Okay, because it can be in a superposition. So these people call it as a quantum parallelism. Okay, so this will give an advantage. Okay, so this is one specific kind of a problem where quantum computing can give an advantage. Okay, why is that? Because one of the fundamental properties is that the qubits can be in a superposition. Okay, that's the one thing. There is one more thing. Maybe you can go back. Yes. Maybe this is one more property called an entanglement. Now maybe when Santosh is speaking, right, he's talking about these particles. Right, he's saying that okay, one particle is here and another particle is there. Now why he brought the particles? Maybe at the time you were wondering what to do with the particles in computing. As I told you, right, because we talk about these atomic particles, because they are the underlining thing. Okay, you are actually playing with these atomic systems. Okay, now what happens is that you see that particular thing here. Let us take that 2 qubits. So this is the first qubit. Okay, the first qubit is in a superposition, and this is the second qubit is in a superposition. But what we do is that, say for example, I'll just try to bring it physically. Okay, mathematically it is very easy to look at, but physically what happens is that you take 2 electrons because these could be a qubits. Okay, and you do some kind of an interaction, and let them make entanglement, and you take one of the qubit to maybe far end of the gate, maybe far end of the Bangalore, from Tumkur to Bangalore. And you are here, okay? So what you do is that if you measure your qubit right, okay, it will have an impact immediately on the other qubit. Okay. Now, so how does this useful? It is useful for some kind of a communications. Okay. Now, so maybe computing, right? Entanglement is a very important role here. Okay. Now, these are the two fundamental properties in a sense, right, to how classical computing is different to the quantum computing. Okay. Now to summarize, right, so what are the takeaways from here? Now quantum computing is different to classical computing. Okay. You have to play with atomic systems. Okay. And the rules are not slightly different, actually they are entirely different to the classical computing. Okay. To certain problems, say for example, where we can take an advantage of the superposition and entanglement. Okay. Now you have to look at the problems. Say for example, drug discovery, as I mentioned to you. Okay. Now similarly, like a financial modeling. Now the financial modeling problems, right? We can actually bring back to this kind of a quantum computing problems. Okay, so then you can actually solve these problems very faster. Okay, now to just before wrapping up, I'm giving to Santosh. Okay, I spoke about cryptography, right? So one thing the governments are very worried about. Now let us look at you go to the ATM machine, right? Now ATM machine, every ATM card has a pin. Okay, so you know the pin. And when you enter the card, it asks for a pin, and right? When you enter the balance, okay, this amount I want to withdraw, it asks for a pin, right? Now, you see, it goes to the bank server, okay, it checks the pin and says that, okay, this person is the correct person, you can give the money, it will give the money, right? Now, generally the cryptographic rules are something called RSA cryptography. Okay, so in a simple sense, what to do is that, let us see, come back to the 5 into 3, what is the answer? 15, right? Multiplying is easy, then factoring is, giving a number say 15, so tell me the factors, 3 into 5. Okay, it's slightly complicated, right, for 15. Now take it to like a very large number. Okay, now multiplying two numbers is easy for your computers. Okay, but to do the factorization, right, it's not so easy. Now this is the underlying technique of this RSA cryptography. Okay, now if you want to, so they have a very large bit number there. Now we have to do the factorization. So it goes to the public channel. It is not so easy to decompose into the factorizations. Okay, now that is what the security does. Now but with the quantum computing, so there is something called Shor's algorithm. Okay, what it does is that it it has an exponential speed up compared to the classical breakdown. Okay, now that is where actually all the people are a bit worried. Okay, now because still the technologies are under progress. Okay, we don't have such an robust quantum computer to break a high bit numbers. But once you get it right, you can break everything. Okay, now also look at, say for example, so that is where governments are actually investing. Private players are investing. Now how to make it more secure? Okay, so they're coming with this so post-quantum cryptography methods, even quantum cryptography methods. How do we actually make secure them? Why is that? Look at this, for example, say for example, US government. In the World War II, they have some secret information. They made it confidential and they secured it, right? Now you got a quantum computer which can break it very fast. You see, it can, what it will do is that you say for example a Chinese player, he comes and just breaks that whatever the information and he can get that information back, right? Now this is where governments, the private organizations are spending a time. Okay, they want to have these kind of capabilities. Now, why you want to look into this thing? You see, this is an advanced technology is coming into the picture. So you should look into this. Okay, what can we do with these kind of skills? Okay, so that is where as a students, right? Now you are about to finish your courses, right? Now this is where you have to remember these things. Okay, there is some advanced technologies are coming. Okay, how can we learn this thing? How can we make better of it? Okay, so that is very important. Maybe I will invite Santosh so he can wrap it up.
Okay, just to give the problem sizes we are trying to address in quantum, I will tell you one small story. In one kingdom, there was a king. Okay, he wanted to invent some new game, and one guy came up with chess. You all know that chess was developed by India. Are you agree with me, right? Chess was invented in India. Okay, so he came up with the chess. So now he wanted to reward the person who invented the chess. What could have he asked? If you were the inventor of the chess, what would have you asked? Come on, whatever you want, you can ask. You want the Prime Minister post? You want to replace Modi? Or you want to replace Trump? Or you want to replace the king itself? You can tell anything. What your wishes. Nobody has the wish. Okay. Okay. That guy who invented, he just smartly asked that every square you give me, say first square, there are how many squares in a chess board? Sorry? Okay, we have to get the chessboard and count, is it? 64. You are the intelligent girl. I really appreciate you. There are 64 chess squares. So what he asked was, the first square you give me one rice, one grain of rice. The next you double it. The next you double it. Simple, right? 1, 2, 4, 8, 12. It's easy. So king also thought, yeah, it's very easy. I can give any, I have so many grains of rice, I will give. By the end of 60th square, how much rice he would have got? Can anybody guess? Huh? More than the? You don't imagine, the rice he would have accumulated is more than what we are producing all over the world now. It will be 18 quintillion ton. So how smart he is. That kind of problems we are addressing using quantum. HPC, yes, of course, as Naresh was telling, we can solve the problems, but not a problem of this big size at a faster time. So that is called as hardest problems, NP hard problems they will call. So these kind of problems we are trying to address using the quantum computing. Okay, so why quantum, why now? Because it has given the promises that it can be used in multiple things. For example, material discovery. What kind of material you would like to discover? I have given a hint there. Chip designing, yes. Chip design, you all know that they will use silicon wafers, right? Many other rare earth metals they will use. Okay. What about your batteries? What kind of materials they use in batteries? Lithium ion. So is there any other batteries which can be better used? Say for example, yes. No, not solar based. For example, where the lithium ion batteries, when you charge, it won't last for a longer time, right? So is there any other, say for example, they are trying to use aluminum as another replacement for lithium ion. Okay. So there are many other materials wherein they wanted to simulate, understand how its behavior and apply it so that you get better batteries, so that your EVs can draw till Delhi, not just Mysore. Okay. So next, climate modeling. Of course, we want, like I was driving from Bangalore to here. I did not know that suddenly there will be a rain in between, right? Even the weather forecasting personnel, they did not announce that there will be a rain, right? We know that there is a monsoon, but it is a general notion wherever the monsoon comes, but not to specific area where it comes. So using quantum, we can solve those things. Healthcare, I have already told, you can discover the cancer. Many other healthcare devices can be built using quantum. Then of course security, we all know that we just discussed there will be encoders, decoders, even my colleague he has touched upon the security, how a message if we want to now communicate to other party, we will use RSA encryptions, right? For example, how many of you have done online income tax filing? I think professors would have done, but not the students, and very soon you will also do. You use some kind of cryptographic keys, okay? So that is where they use, and these quantum computers can challenge those keys and break and get the decoded information. So how to safeguard? Again, quantum will give you the solution also. It's not that it does not give that. Next slide. Okay, now here I see the diverse audiences. Is quantum only for certain class of people? No. Quantum is for all. It varies from students to faculties, entrepreneurs, even the government. So how students can help? Now you are in MCA, where you use a lot of softwares, algorithms, flow, designs, right? So you can develop some novel algorithms to solve some particular things. Say for example, you first start learning the basics, okay? Basics of quantum mechanics, how you encode the classical information into quantum states. Well, there are different ways. I will not go detail of it, but of course you can do that. And where are the quantum computers available? Right now there is no quantum computer available. I mean, there are few quantum computers, but it is a bit costly. Earlier, how they used to do? They used to do through simulator. Before flying a flight, will anybody trained flying flight, will they give directly the flight or no, right? So they will do through simulators. So there are a lot of simulators. You gain the knowledge through simulators. You develop some of the algorithms, okay? Then get into the workforce of the entire quantum community. Now the faculty, how they can be part of this? They can bring the courses, the undergraduate courses or the electives as quantum computing or quantum communication or quantum technologies itself, and they can build this workforce. And for entrepreneurs, of course, they can invest on some of the products. Say for example, these sensing devices can be, or QKD, they can take it to the market. Many will develop, but it will not be going to the market or to reach to the common man. So that entrepreneurs as a company, they can do. And of course government, there is a big support, as my colleague was telling. There are various schemes, project approvals, proposals can be submitted and they can be got. Next slide. So how to get started as a student? You can make career paths in, see, it is a diverse technology. It is not that only physics is required. No, not like that. Even an engineer, electronics engineer is required, a computer science engineer is required, and a mechanical engineer is also required, where he designs the computers, right? So you can take online courses, get certified, participate in some big events. For faculties, integrate the quantum courses into UG, PG, then focus on some research areas, then collaborate with national labs and industries. Then for entrepreneurs, they can develop hardware, software tools, then algorithms, leverage incubators, research labs, and through government, of course, there are supports used from NQM, that is National Quantum Mission, and through DST along with AICTE, you can set up the undergraduate courses in your colleges. Yeah. Next. So quantum revolution is coming and it is here. Whether we will catch up or we will just watch it and be part of the audience, or we will go along with that, is our left to us. Now I will leave it to you, how you can take it further. It is up to you. Thank you.
Thanks a lot for both the invites. I please invite Renko Prasad to thank the guests.
That is that, like you will be, for example, I will be sending a particle to you. It can be destroyed by itself, right? Like it has, everything has an expiry.
Yes, of course. It can expire. Say for example, the light, where I encode information through light, it cannot travel for a longer distance. Of course, in the classical world, there are repeaters where you copy the data and again resend it. But in quantum, it is not like that. So there are still, the technology is developing. how to bring in these repeaters, okay, where I can travel, make this the communication happen for a longer distance. Of course, there are test beds where they have demonstrated few kilometers. Now they are working for a longer distance, like 2000 kilometers. Any other questions?
Sir, actually, in the Hanuman Chalisa, the distance between moon, sun and earth, it's calculated in the one verse. How they were thinking at that time? That is, I am talking about the Vedic astrology and the quantum computers or something like related to that. How or believing or facts are relating any projects are running in the CDAC?
Not in kind of Vedic, decoding the Vedic verses and finding out.
There is a verse like Yuga Sahasra Yojana par Ban,
Yes.
Leelayev Tahi Madhura Palajan.
Of course, sir, like our ancestors were very intelligent. They knew that the astronomy, that's what I showed you, know, even before that we knew the distance to moon, even our solar system is not round, it is in LA, eclipse. All those things, yes, we had known that. So maybe they use these kind of quantum advantage or I don't know. But now it is coming back. Say for example, if we go in the wheel, where once we are down, we will come back. So it is like that. We are trying to see how olden days people used to do this computing or find out the things. We are going back to that era.
Any research is going on in that area?
Right now, no, sir. Right now it is purely in terms of classical physics.
CDAC is offering any course in this area?
CDAC, of course, they don't have exclusive course on this area, but you can have a kind of an FDPs or some course, not as a course, some talks in that way, but exclusive course is not there.
IELTS and MOUs with the colleges, sir?
That can be, but as a premier R&D under the ministry, we are entitled to have the MOUs with some level of NR ranking-based colleges, not with everyone.
You are improving the already improved ones. Tier 2 cities.
Yeah, I mean, it is said to come from the government. We cannot do anything, sir. It is a mandate given by them. So there are NIF rankings for each college. You might be aware of
Yes.
that. So based on, it should be like below the 100. That is where we have to work on it.
Thank you, sir.
Any other questions?
So the question is that GPU, whatever we are using now, it is based on the HPCs?
Yes, it is based on HPCs.
Okay, whatever we are going to use the cloud like Azure or this, they are developed the HPCs?
Yes, they all, again, like how my colleague and Deepika was showing, they have set up huge data centers with these servers, where they will have multiple GPU cards, CPUs, different cores. For example, your laptop would be of 16 GB, but these servers, the memory itself will be 1 TB. It's an order of that humongous, 1 TB. The cost of those servers are very huge, so where the common man can buy the power which it utilizes, not just the power, it has to be cooled also. It will create a lot of heat, so it has to be cooled. So cooling also draws more power. So that is where these kind of AWS have come, that they will set up, they will offshore whatever it is required. Not that you need to set up the whole infrastructure.
And one more question, sir. Like, see, in government institutions like ISRO or in a lecture, so they have a lot of data. So how they are going to say whether, I mean, this we know that Azure, AWS, they are from US-based companies. So do we have any Indian this to say, because it's a data is confidential?
Yes, data is confidential, of course. Some of the labs where the data are very confidential, they don't use this AWS Azure at all. They have their own infrastructure set up and they use those infrastructures. Only where it is not critical, they might offload to AWS. Again, there are policies which have been framed that the data should not leave the country. So what they do is computing they might do somewhere else, or even they set up the systems at India and they will offload to us. Any other questions? You have one? Okay. You have one question? No. Thank you.
Thanks, Dr. Santosh. Thanks, DrNaresh. I request all of you to give a big round of applause. It's so inspiring, right? He just took the topic from out of the sky, right? And he made us comfortable, right? So they made us comfortable both from applications as well as from technical perspective. This is what is all about, connecting the dots. It's not about learning individual things. This is what we should be focusing on. That holistic perspective, right? If we are able to understand the individual components, that's what we do when we are learning, right? At college, right? What is that? Why CPU used for? Why memory used for? Why hard disk is for? Is being used for? If we are able to connect the applications, right? That profiling being called. Say for example, any big say database application, it requires more memory, right, on the database side. For any finance modeling, we need more CPUs. That application profiling, right? So when you just go to a mobile store, they will ask what is the purpose and how much is the budget, right? So depending on if you are more used on camera, they will suggest. So that's the whole, you should get that big picture, right? That's what they provided. I'm really happy that they made us so comfortable, and I will tell you, Santosh, AI Kshetra is for leaders. Okay, we are going to, stay ahead of, right? So because our process is, say for example, the C language took around 1 year or 2 years max to develop. We won't be spending, 1 year to learn. Our target is to learn in 100 hours and then deliver, and then move on to the next technology. So we want to have students to take exposure to all the technologies. They should be able to connect the dots and deliver, right? So we are not afraid of AI, we are ahead of AI, and you guys inspire us. Thanks a lot.